So now that we've done this, we need to make this less icky. Okay, this gradient descent function is very icky. And the way that we're going to do this is we need to replace all of this for loop business with some vectors. Okay, this is just way too messy. I do not like this. So here's the key clues that we're going to use to be able to do this. I've left the key clues in the comments. So when we're doing this gradient function, we're computing this gradient right here. Yeah. And the gradient, remember, is just, all of these partial c by partial theta, 0, 1, 2, 3, 4. Well, we have this right here. And notice that when we run this function, there's some variables I need to initialize. Let me just make sure to do that. Up here, that's good. Up here, remember sometimes, Kaggle's weird. Don't worry, just rerun. All right, here we are. So we're getting back this gradient from the function, the icky function right now. Notice the gradient, the output we're getting back is an n by 1 vector. N is the number of input, the n is the number of input features, also the number of parameters, because there's one parameter per input feature. You can see 1, 2, 3, 4, 5, and that makes sense because up here in the data, we saw there were 1, 2, 3, 4, 5 input features, 5 columns. Okay, that's fine. That's the output. And notice here we have these two vectors that we're using. So the cost by pred, so the cost by the prediction, that's this term right here, 2 times the prediction minus the label. And we have this m by n vector. So m is the number of examples again. M by n vector is this one right here, where we pass in, just x, which is this table-ish thingy that you're seeing, m examples and input features. And, we get out the output of the sigmoid derivative function for each of those individual x values. So the key to what is called vectorization, using vectors, using vector-based math in this gradient descent function, the key is to look at these dimensions. So the dimensions of these terms that we're using, m by n, that's the size of both x and this term, sigmoid out, this term, sigmoid out by sigmoid in, that derivative. And m by 1, I've got to look at these dimensions and the dimension of what we're trying to get out. This is a little bit hard. So it's a little bit hard to say, okay, how do you get from, say, m by 1 and m by n, and also x itself is m by n, it's being used here. How do we get from that to just n by 1? Especially when I'm saying it, Zuyu, I bet it's just like, what? Why is he saying all of these weird terms? It does take practice. So I'll try and break this down in steps, but don't worry. It takes a while to get the hang of this. Don't worry if it doesn't make sense at first. The first thing that you could always do is do what we just did, which is just, for loops and just try and translate the math into code as literally as you can. And you'll get out some icky results, but you'll get out some results. The next thing that you can do is what I did here, where you notice the dimensions of all of the inputs and the outputs. So each of these inputs to this algorithm, and also, x, we're also using x. And then over here, I noted the output, what are the dimensions? So you can use dot shape for that. Feel free to always go like, oh, gradient dot shape, and it will like give you the dimensions that you need. That's the second step. Note those dimensions. The third step is grab a piece of paper. Okay, I'm not kidding. Don't do this in your head. You want a piece of paper. We don't have paper, here in our notebook, but luckily we have me drawing out an image. So we have over here this 1 by m matrix That's over here, n by 1 vector, sorry. And we have an m by n vector, that's this one. And I was like, okay, we have these two things, we have to combine them somehow. We have to use some sort of vector math, some sort of matrix operation to get from these two things to a n by 1 vector. The n by 1 vector is the output, yeah? I hope this is making sense. So that's the third step. Draw the thing out on paper. You don't need to fill in the numbers, just draw out the dimensions. And then you're gonna try and think about, okay, like, do I add things? Do I subtract things? Do I multiply things? What do I do to get from these input dimensions to this output dimension? Here, maybe it might help if I took the transpose of this matrix, okay? So remember, transpose just means if I have, the dimensions like this, flip it over. So from an m by n matrix, I'm going to an n by m matrix. Took the number of columns, made it the number of rows. Took the number of rows, made it the number of columns. It just flipped. Now here, I hope you're noticing something. So if you're very confused right now, you need to go back and review the matrix operations lesson. Hopefully, if you do that, you'll remember one thing that I said about 5 or 6 times, which is there's this one operation, useful operation that you should be thinking about right now, where the number of rows of the first vector, it needs to match the number of columns of the second. Now, if you remember that operation, it's the dot product. What's the dot product going to do? Let's just think about this. So if I was able to draw in an X here, let's see if I can annotate my screen temporarily. So that's like my dot operation. Yeah. What's going to happen? It's going to take each example in this first matrix, in this first vector, and then multiply it by every single row in the second. Yeah. So what we're going to be left with is, this first element multiplies with this first element in this row. So, then like the next one, and next one until you get to the end. Yeah. And now all of that is going to give one number, which goes in this first position here. Then what's going to happen? We're going to do this all over again, but now for the second row. And now that is going to go in the second position here. And we're going to keep doing that for all n rows here, which is going to result in me getting n elements, just as it indicates here. So the dimensions align. Now that's the first important part. Make sure that the dimensions work. The next important thing is, do we actually want to be doing all this? So if we do all this, will it actually do what we want in terms of the algorithm? Let's try and take a look. So in this formula, what we're doing is we want to compute this inner term, then sum over all of the examples, m, and take the average across all of them. And that's going to give us the first, the first term. Then we're going to do it again for, j equals 1, 2, 3, and 4. So here's my hope. Hopefully, when we're doing that operation, remember it's a dot product operation. What a dot product operation is good at is it's good at summing automatically. So we want to be summing over the examples. Is that what's happening? So every time when we go through, this m long vector, we're going through each example and we're multiplying it by this all of these columns here, which are m columns. So we're multiplying all of the values corresponding to all of the examples for this vector with all of these values corresponding to the examples for that vector. And we're just summing them all up. That's what we want to do. I know this is bizarre. It takes a little bit getting used to. So I'm going to show you, what this looks like in code. But keep in mind the key idea here. What I'm doing is I'm replacing this summation. Instead of having a for loop here, I'm summing, I'm multiplying and summing all of the values of this vector that correspond to all of the examples with all of the values of this vector that correspond to all of the examples. And the multiplying part just means, I'm multiplying all of these values with all of these values. I hope that's making some sense. Multiplying all of these values with all of these values, and I'm summing them at the same time. Here's what the code looks like. So in the vectorized implementation of the gradient function, not the icky implementation, we still need to get, our values m and n. So I'm getting the values I need. Then I'm still computing these two vectors in the same way that I computed them up here. The exact same code right here. I'm computing these terms and these terms, and I'm doing them with like all of the x's and all of the predictions and labels at the same time. And in the icky implementation, then I went through, all of the input features and their corresponding parameters with this, with this for loop, and then all of the examples with this for loop. Now I'm not going to use for loops. I'm going to use vectorized code. So now that I've computed these same terms, here's what I'm going to do. First thing, I can show you what these two things look like. So actually, ignore these two lines for a second. Ignore these two lines for a second, just 1 second. So I got these same lines here, and here's the first part of the operation, the part that I'm highlighting. I am using np dot dot, the function that does the dot product, to sum this m by 1 vector, you see, cost by pred, that is m by 1, and this sigmoid out by sigmoid in vector, which is m by n. Now, depending on, how you pass in the values and your code, sometimes you find that you're going to get an error when you do these dot products. I'll show you an example of that earlier, but what I had to do was I had to play around, Do I take a transpose? Do I not take a transpose? Do I take a transpose here? Do I not take a transpose? Sometimes you have to play around a bit. By the way, this is the way that you take a transpose in Numpy. You add a dot t. That would that would be a transpose. If I run this, you'll find out you'll get an error, shapes not aligned, something like the dimension 0 is not equal to that. What that just means is, the way that you passed in your matrices to the function, unfortunately, the dimensions didn't match up, right? The number of rows of the first was not equal to the number of columns of the second. So honestly, I like sometimes just, do some iteration. So no, this time it's working, and I tried a few different combinations out to figure out, which one should I transpose. So this is what's happening over here. These two are being multiplied with a dot product, and I'm getting back a n by 1 vector. Remember, that is like, multiplying these values, all of them at once, and these values, all of them at once, without using a for loop. However, I still have this business over here. I still have to multiply all of these x terms. And x, just like, this sigmoid out by sigmoid in vector, that's m by n, x is also m by n. So when I'm multiplying all of these values, before, I would use a for loop, select each element within the matrix and multiply that. This time I don't want to do that. This time, what I want to do is, since I already, combined these first two vectors to get an n by 1 vector, right here, this highlighted code part, that's now an n by 1 vector. What I want to do is I basically want to take this, this m by n vector, x, and turn it into an n by 1 vector. So from m by n to n by 1, or like conversely, you can also say m by n to 1 by n. That's what I want to do. What does that correspond to in real life? That corresponds to taking the sum. You had m examples and input features before. Let's imagine you squash that. So now you just have 1 by n. So you added up all of the values for all of the rows. Here's what it looks like. You take all of these values, for each example and add them all up so that you're left with, just one row, and it has the sum across all of the examples. I know it's a little bit confusing. I hope some of this is sticking, but if not, it's all right. It is confusing. So how I can do that is with this function np.sum. What np.sum does is, it adds up a lot of values. I am passing in x, so the m by n vector, x was m by n, and after I sum it, I put in an axis. What the axis means is it's kind of like, imagine like x and y axis, this direction and this direction. So this is like the first direction, that's 0. That's the number of examples you just saw right here. You saw this table-ish looking thing. So this is the first, this is the 0th axis. It goes up and down. It's the number of examples. This is the 0th axis, first axis. First axis is each input feature. Again, I experimented, which axis to choose. I wasn't sure. So I was like, okay, what happens if I choose different directions? So let me show you how I experimented. I just print, the shape of x and the shape of x sum, the output I'm getting. So here it says, okay, x is 4,238. That's the number of examples by, 5 input features. And, the sum I'm getting out is 5. That is what I want. However, originally what I tried was I just, did np.sum x. And when it's like an empty bracket, that just means this is a scalar. This is one number. So I can actually show you what number it is. So it just added up every single piece of data, in there, and it got one number. So that's how I knew, oh, something's wrong here. I don't want to just, I don't want to just do np.sum. I got to choose one of the axes. And then, I can try and, choose the first axis, and it's like, oh no, so many errors. No, there's like different shapes. And I'm like, hey, that's not what I want. I wanted to, sum across all of the examples, but I can still see I have 4,238 examples. So there's a little bit of iteration involved. Anyways, in the end, I'm going to go from an m by n vector, so m by n, to just like a 1 by n vector. Remember, that's the same thing we got here, 1 by n. You see, 1 by n, 1 by n. So I can actually multiply these two things together now, element-wise multiplication, because these are both 1 by n vectors. And that corresponds to me. Here's the crazy thing that I did. I broke up this summation, okay? I broke it up into, let me show you with annotation. I broke it up into this part, yeah? And then I added on this part. So what I did was, instead of doing this part element-wise, I used the dot product to basically get the summation operation attached onto this. And I'll show you what that looks like in the code again. Let me stop annotating. Let me show you what that looks like in the code again. That was this first part. So I did a dot product. The dot product not only multiplied these two things, and by the way, like I don't need to multiply the one is just one. So it multiplied all of this business and it summed it at the same time. Then I broke off this part separately. So this part, I just summed it using np.sum, okay? And then I multiplied it with the result of like this first product. Why does that make sense? Just think about it. If you have, a multiplication of, and then you're adding together the results, well, if you think about basic math, if you multiply 2 times 1 plus 2 times 2 is the same thing as just adding together all of the stuff inside and then multiplying by 2. So 2 times 1 plus 2 times 2, that's the same thing as saying 1 plus 2, that's 3, and then multiplying 2 by 3. If that sounds really weird, it's called the commutative property. You can search it up. So anyways, in the end here, I broke up my calculation. I got the answer that I wanted. So I used vectors to compute all of this business. And I just divided by m at the end. Gradient divided by m, because I'm taking the average. And that is the vectorized implementation. Yay, it works. So I hope you appreciate this. This is a lot less work, 1, 2, 3 lines of code, and I could make it even shorter versus all of this messy for loop stuff down here. So I hope you appreciate this a bit. Now, if you don't understand, it's fine. You don't need to. You can always fall back to the gradient, icky implementation, but they both do the same thing. I hope that's making some sense. But if not, don't worry. It's all right to not understand. It is tricky. Now, with that being said, we are done. That is the last part of our algorithm. Look, at the beginning, we had our to-dos, so we got the data, we made our helper functions, we made the feed forward and the cost function, we made a compute gradient function. Last thing we need to do is just, the gradient descent function. And the gradient descent function, well, that's pretty simple. You just repeat this a bunch, take the data values, subtract the learning rate, times the gradient, but we don't need to compute the gradient. We just made a gradient computation. So we're going to use this function over here. The way we're going to code gradient descent is this. We're going to use this parameter, this variable, the number of iterations, because remember, with gradient descent, we want to repeat it, 100 times, 500 times, 1,000 times. We want to repeat this a bunch of times. So we're going to create a for loop. So this for loop, what it does is it just repeats however many times we pass it in the number of iterations. So for example, it repeats 100 times. Each step of the for loop, I'm just going to print like a little period with, no space at the end, because it's just going to show like a trail of dots every single time it does an iteration, just to see progress. And look what we're doing. So here we're getting the prediction, because for the gradient implementation, we need to get these variables, the prediction x and y. So we're going to get the prediction with our feed-forward function, which we coded up here. We're going to figure out, with this current prediction, what is the cost? And we have all of these variables, x, y, theta. We're going to push the cost to this array every single time. We're going to append it to this array. Why are we doing that? We want to track the cost over time. So when we're making these changes, when we're making, these subtractions to the data parameter, we want the data parameter to be getting better. We want these parameters to be better able to predict the output. And the way we measure that is with the cost. So that's why every single iteration of the gradient descent function, I'm also doing this. I'm also getting the cost and saving it so that at the end I can go back and check, okay, is the cost actually decreasing over time? But for the gradient descent calculation, it's just literally these two lines of code. So let me put in a comment that make sure you can see. This is just to monitor cost over time. And instead of time, I'll say iterations, because technically we're just doing this every iteration. And here, this is the gradient descent part. How are we doing the gradient descent part? Well, we just call our gradient vectorized function. We pass in, the prediction, which we needed to generate, and x and y. It just calls this function, and it returns the gradient vector. Remember, the gradient vector looks like this. It has 1, 2, 3, 4, 5 values. And data also has 1, 2, 3, 4, 5 values, as you'd expect. Once we've gotten the gradient, then it's literally, what you see here. What you see here. Theta is equal to theta minus the learning rate times the gradient. That's literally what we wrote. Theta is equal to theta minus the learning rate times the gradient. Literally what we wrote. At the end, so this, you see, is adjusting the theta values every single iteration in our number of iterations. And, we're checking the cost, we're monitoring the cost over iteration. So we want to, return one, the optimized data. So after, all of these adjustments have been made to the value of data, what is the new data value we have? And we're returning this cost history because we're going to monitor that to make sure that data is going down over time. Sorry, the cost is going down over time based on the data we choose. Let's test it out. So that's a gradient descent function. I hope that's making sense. Not too bad, especially this step. The hard part is just getting the gradients, but all of the rest, that's pretty intuitive. I'm just going to set a quick learning rate parameter, just to have one for now. Remember, we can, adjust this for, optimizing the algorithm. We're going to talk about this later. I'm also going to set 100 iterations. So the algorithm is going to run 100 times. It's going to perform this test 100 times, this step. And here I'm passing in all the values. I'm going to get out the data and the cost history. And I'm just printing it here so we can see, is the cost history actually getting better over time? So you see it did all this. Now, one thing that I want to make sure to do is I want to make sure to get a fresh data value, because what I see in the code here is that the data value that we have, it's been modified in the previous steps, gradient descent and all that. So I'm going to set a random data value. Remember, we need 5 parameters in data because that's n. I wouldn't usually hard code it, up here. I got the number of features. It's the same thing, 5. That's the number of features in this case. So I'm going to set data. I'm going to initialize it randomly, some random parameter values, and hopefully the algorithm optimizes this so that the cost gets better over time. So let's run this. And you see the cost starts at 0.84, and then it goes down to 0.83, 0.76, 0.58. Yo, quick, yay. And then in the end, the last one that we get is 0.48. So that is literally doing AI. Okay, this is what doing AI means. We have formally done AI now. We took a problem, an optimization problem, which is where we have a cost, and we brought the cost down by adjusting the settings, the parameters of the algorithm. And this is kind of non-visual, so I'm going to do one last thing. I'm going to show you a very important graph. We're going to study this later in theory part, but we're going to make the graph with matplotlib. That's a graphing library in Python, a graphing module in Python. If you're working on a local machine, you'd have to install this. If you're working on Kaggle, your life is simple. They already did it for you. So here's what I'm going to do. I'm going to plot this over the number of iterations. So I want to see, a visual way of this of representing this information. What I'm going to do is I'm going to call matplotlib.pyplots.plots, and then I have to pass in like an x and y to plot. So for the x, here's what I'm going to do. I'm going to create a range. Matplotlib can take a range. It takes lists of data. So I'm going to, make a range, and it's going to represent all of the iterations. So I'm going to pass in the length of num iters. Or actually, sorry, num iters is just a number, so I just need to pass in num iters. So this is going to be the x. Here's the x if you want to see like what it looks like. It's a range going from 0 to 100 representing the iterations. Y is just going to be, our cost history, the cost going down over time. So this is empty right now just because, I haven't put in any information. So Y is just going to be our cost history. Cool. So I'm going to put in X and Y in matplotlib.pyplot.plot. And you can see, my screen's a little bit dark here. You can see that the cost started off up here and then it went down. Yay, that's what we want. So officially, we are doing machine learning. We are doing AI. That is the end of this long lesson. Now, what I'd recommend to you a lot is go back and review the parts of this video where I explained the gradient ICI function and the gradient vectorized function. This is the hardest part. And if you don't even, if you're lost with the code, go back and, review the, this equation right here and this equation from the lesson number 8, and make sure you really, really understand this. If you want to understand AI, this is the part to understand. So with that being said, this is the end of this lesson. I'm going to stop and make sure all of us have some time to review, because I want you to review this. You don't just have to look at my resources, search up things, you have questions. There's this amazing Stack Overflow thing. If you don't know that site, just go to Stack Overflow, see what other questions people have about this. Go and search for the right resources. Make sure you understand gradient descent. All of the other stuff is really easy. The gradient descent is the hard part. And more specifically, this part is really easy. The backpropagation algorithm, the algorithm to get the gradient, that's the hard part. So that is your task. Maybe we might have some Q&A, and I might throw in a video after this with like FAQs, but that is the end of coding your very first algorithm with Numpy. Yay, you did it. We have officially started doing AI. I hope you're feeling great.